to the vesicle. Well, what he did is put a supply vesicle, but of course if he didn't do anything else, as the water level in the supply dropped, the speed of water coming in would decrease. As more water was added, the speed would increase. That would be a very unreliable timekeeper. So he devised the system where he put a plug in here, which was a float, so that whenever the water dropped, it let more water in, but whenever the right level was reached, it shut the flow off. It's an elementary form of negative feedback, but interestingly, it took approximately, well, over 2,000 years before this idea became an accepted, well-understood idea of design.
For the Greeks.
Yeah, but there's a lot of people in between who individually, as they needed it, came up with the idea for things like regulating windmills, for regulating furnaces, but then Watt's design for the steam engine, the governor for the steam engine, was one more realization of a negative feedback system. In the wake of that, James Clerk Maxwell provided a mathematical analysis of the behavior of these governors. That's where the equations actually come from. But still, it was a long time before the idea became general. It's with such things as the engineering of heat-seeking missiles and other negative feedback devices in the 20th century, and the emergence of the cybernetics movement, which made, originally the idea was circular control. Feedback was the key idea of their system, and what they pushed very hard was it was a common principle to the organization of biological systems and humanly engineered systems. But what I want to emphasize here is that even once the notion of negative feedback starts to become a regular tool for engineering and regularly recognized, say, with the work of Walter Cannon and in his notion of homeostasis as a principle of the organization, particularly of the autonomic nervous system, it still was viewed as primarily a system for keeping a system in a target state. What people recognized early on, but recognized initially as a nuisance, was that negative feedback can create oscillations. We all are familiar with this. If you have a thermostat hooked to a furnace, once the temperature drops, the furnace comes on, the temperature rises above the target level, that until it reaches the point that the thermostat turns the furnace off, then it drops below the target level, and people often will complain about it. They complain about it so much that engineers have worked very hard to develop new designs for controlled thermostat or furnaces so that it will minimize as much as possible, dampen as much as possible oscillations. Similarly, in the acoustics industry, oscillations are typically a nuisance, and what one wants is an optimal way of dampening an oscillation so as to get regular performance. So oscillations are something to get rid of. In biology, we'll see that oscillations, far from being something to get rid of, are actually critical to the operation of many biological systems. But we still try to ignore them as often as possible. My favorite biochemical reaction is the manufacture of alcohol from sugar fermentation. But it is standardly represented as a linear string of reactions, taking us from glucose through a number of phosphorylated intermediates until the production of pyruvate and eventually ethanol. So the traditional way is to view it as a sequence of reactions. I, early on, not knowing why I was interested in this, wondered what happened if we took this representation and started to close these loops where ATP is used first to phosphorylate the compounds and later is formed by a transphosphorylation reaction and to capture the energy from the reaction. Well, if you close those loops, you see a very different picture. Rather than a linear string, you see ADP forming a cycle, and that becomes part of the structuring of the whole system, NAD and NADH forming a cycle, and the compounds that are the major players in this picture figure as steps in the movement of molecules through a more complicated integrated system. Unknown to me for 30 years of spending my life thinking about fermentation as a primary biochemical reaction is the fact that this system was one of the early ones to be identified as an inherently oscillatory system, at least under certain conditions. It's partly due to the feedback system in the system. It's also due to the fact that this enzyme right here is a allosteric enzyme, which is introducing a nonlinearity in the system. But in fact, at least under a variety of conditions, arguably in living conditions, one has an oscillation going on within this system. I'm going to just very briefly touch upon what has now become my favorite oscillatory system. I spend a lot of my time thinking about circadian rhythms. 15 years ago, 20 years ago, some key breakthroughs were made in understanding how it is that we're all plagued by the fact that we just went through time change and our bodies take a day or two to adjust, but if we have to travel to Europe, our bodies take as much as 2 weeks to adjust to the change of time, that there is an endogenous oscillator in us that manages to keep approximately a 24-hour oscillation. What was discovered in the 1970s and then fully worked out, began to be more fully worked out in the 1990s, is that what we have is a gene period pair which is transcribed into an mRNA, which is then translated into the protein pair, which then serves as an inhibitor of its own expression. So we have a feedback loop whereby a system is designed to maintain an oscillation that approximates the 24-hour day. What one needs to do once one began to develop the story of what the molecular constitution of the mechanism was. By the way, this is horribly underestimates how complicated the system is. We're now talking about minimum of at least 30 genes and proteins in the system and probably 3 different feedback loops, 2 positive, 1 negative. What one does is needs to figure out not just what the parts and operations of this mechanism are, but will it oscillate? Well, to do that, the only way to do that is to actually figure out how are you characterizing each of the chemical operations in the mechanism, and then write a set of differential equations and see whether, in fact, given reasonable parameter values in those equations, one gets an oscillation. Well, what in fact one gets in this system under reasonable parameter values is what in dynamical systems theory is known as a cyclic attractor. It's a system whereby if the system is perturbed either inside or outside the circle, what we're representing here is total amount of pair and pair's mRNA. So we're taking 2 variables in the system, showing that they change in a regular relationship with each other. And if the system is either pushed inside or outside of the attractor, it moves back into the attractor. So what we're doing here is combining the tools of dynamics, differential equations to model the system, and the use of representations such as cyclic attractors, with an understanding of the molecular constitution of the mechanism, and the 2 are working together to give us an understanding of how the phenomena is emerging. Now, let me briefly return to the criticism that Van Gelder made of classical models relying on representations, in his claim that if we really just use a system like the Watt governor as our model of a cognitive system, we can do away with representations. Well, actually, if you ask yourself why this governor works the way it does, one of the natural ways of talking, and Gelder recognized it was a natural way of talking, he thought it was a misguided way of talking, was to think of the balls on the spindle arms as themselves representations, and their location in or out as representing speed, which would then be used by a consumer, the linkage mechanism,